Good morning, everybody, and welcome to our International Physics webinar. Today it's our 264 International Physics webinar, and we have with us here today Dr. Christoph Boehme, sir, Professor and Chair Department of Physics and Astronomy, University of Utah, USA, and he has already connected with us. Sir, good evening to your part and good morning here. Thanks for joining with us and thanks for accepting our invitation, sir. So dear viewers and students, I think you will enjoy this session, and the title of this session is Spin-Based Quantum Sensing with Charge Carrier Spin State in Organic Semiconductors.
Hello.
Yes, sir. I can hear you.
Yeah, okay, very good. There was an interruption in the transmission for a second. All right. Are we ready?
Yes, you can. You can continue.
Okay. Sir. All right. So, well, first of all, a good morning to Pabna University. I'm at home. It's late at night in Utah, and it's a great pleasure to present. Thank you for the invitation. I'm really excited. Thank you for coming and for your interest. So the title of my talk, as we just heard, is Spin-Based Quantum Sensing with Charge Carrier Spin State in Organic Semiconductors. So what is our research all about? In a broader sense, the research program in my research group is focused on spin selection rules for electronic transitions. And in the context of quantum sensing, in particular spin quantum sensing, these physical processes, these electronic processes, have found significant interest in recent over the past 5-6 years. So now, actually, one question that I have at the beginning: how much time do I actually have? I assumed an hour.
Yeah, you can talk an hour. No problem.
Okay, all right. So I'll try to wrap it up then by 10 p.m. my time. And I guess that would be also 10 a.m. your time, I suppose, or 9 a.m. I don't know.
So now it's 10 a.m. here, 10:04. Already 4 minutes.
It's 10 o'clock. So
10. Yeah.
Yeah, okay, very good. Okay, so I'll briefly fill you in on spin quantum sensing. That's kind of give you a brief overview and what is all the activity and the excitement about it. And then I'll focus on the kind of the physical systems that we actually study. And then hopefully I will be able to bring this together in my presentation. So let me start with the question of what is a quantum sensor? Of course, what a sensor is, most people know that a sensor is a technical device that transduces a physical observable into another physical observable that we can usually detect or process much easier. So good examples for classical sensors are, for instance, temperature sensors. These are temperature sensitive resistors, for instance, that transduce temperature, a thermal equilibrium observable into, for instance, resistance. And that means we can then transduce this into a voltage and we can measure that. So what's now different for a quantum sensor? And a quantum sensor, first and most of all, is a quantum mechanical system whose quantum mechanical behaviors we utilize in order to probe observables. And in a very broad sense, what you need there is defined in complete analogy to quantum bits as we know them and have known them for more than 25 years now in scalable quantum computers. So there was a person named there is a person named David DiVincenzo, and he wrote down the criteria for quantum bits a couple of decades ago. And so if you want to represent quantum information, you need a quantum bit. And a quantum bit is, first of all, a quantum system with resolvable energy levels and discrete energy levels. You need to be able to initialize this, meaning you have to have some sort of physical process to bring it in a well-defined eigenstate or in general quantum state. then you need to be able to measure that. In other words, you need to be able to read your information. And then it must also be, this is where quantum mechanical properties become important. You need to have the ability to coherently manipulate it. So you have to have coherent control. So these are 4 out of the 5 DiVincenzo criteria. And the 5th one that we know for quantum bits in quantum computers is missing. That's namely the one where you can bring different quantum bits into well-defined interaction states. And instead, for quantum sensors, you basically have to have a quantum bit that interacts with physical observables, those that you want to probe, in a well-defined way. In other words, the eigenenergies, the Hamiltonian of your system, is modulated by these observables. And the idea behind quantum sensing is basically by probing the Hamiltonian, in other words, forcing your system onto a coherent trajectory, which is deterministic, because for as long as your quantum system doesn't collapse, it follows the propagation of Schrödinger's equation, you can learn something about your physical observable. And why is this interesting? Why do we want to do that? Let me give you actually a well proliferated example of a quantum sensor that's actually applied and has found various applications in biology and chemistry and all sorts of scientific environments, and that is the nitrogen vacancy center in diamonds. So people have been studying this since at least the mid-1990s. And if you go down this list of DiVincenzo criteria for quantum sensors, you will see that the NV system, a point defect, nitrogen vacancy in a diamond, a crystalline diamond network, which leads to a paramagnetic a spin 1 state with significant dipolar coupling, all of which essentially creates the kind of quantum mechanical system that meets so very nicely these DiVincenzo criteria. You essentially, you have a probe. And the real advantage now of quantum sensors in comparison to classical sensors is because you probe the Hamiltonian by forcing the system into coherent spin motion, your measurement sensitivity is actually not an inherent property of your transducer, of your sensor system, but it is actually a property of how you quantum mechanically drive your system. And that actually means it's the way you measure that determines how sensitive your measurement is, and not the sensor itself. And that's, of course, a tremendous advantage of these systems. So with this kind of very brief introduction, 5-minute introduction into quantum sensors, what are the kind of material systems that we are studying in my research group? We are actually not working with NV systems. And why may these or are these of interest in the context of quantum sensing? So, and that brings me, as announced in the title of my talk, to electron spins. Well, that is actually what we find in NV centers as well, except we don't work with diamond, we work with organic semiconductors. So what's about electron spins in organic semiconductors? So when you think about organic semiconductors, and then of course we all think about cell phones, basically, that we all use every day. A lot of these cell phones depend on organic semiconductors because the cell phone displays are made of many cell phones. In fact, most cell phones are made out of organic semiconductors. And so when we think about these materials, then we immediately think in terms of OLEDs, maybe organic photovoltaics, and we remember that these semiconductors, these materials have remarkable electronic properties. They're easy to process, mechanically flexible, versatile, meaning you can, just by means of chemical synthesis, you can create a whole bunch of different materials with different quantitative properties. And they are also extremely cheap. It's very cost efficient to make devices out of these materials. Now, this is all known and has caused at least one technological revolution. But let me tell you, when we talk about spins and spin applications, this is totally not the reason. None of these aspects are the reason why we're actually interested. inorganic semiconductors. What makes it really, really interesting from a spin perspective is because these materials are carbon-based or hydrocarbon-based, electronic states in these materials typically have very weak spin-orbit coupling. And the absence of spin-orbit coupling, or the near absence, leads to very usual spin effects in these materials and associated electronic behavior. That leads exactly to the spin selection rules that I mentioned. So to give you on this slide another overview about the work in my research group, there are basically two aspects. One, what you find here on the left is what I list as spin polarization effects that we study. And by the way, where does the spin in these materials come from? I mean, these are not ferromagnetic materials. So spins typically come from electronic excitation. So in an equilibrium state, most of these materials are actually completely diamagnetic. But as soon as you excite excitations, you inject charge carriers, so-called polaronic states, because charge carriers in these materials are localized electronic states. They have polaronic, most of the time, polaronic properties. Then you create paramagnetic states, and now that means you can polarize these materials. And then we basically talk about spintronics. And so amazingly, in these plastic materials, you find spin transport. You can find well-known effects from inorganic spintronics, such as inverse spin Hall effects, the spin Hall effect by itself. You can pump pure spin currents with ferromagnetic injectors. This is very, very interesting. But that is completely separated from what you find here on the right-hand side, and which is the part about which I will talk for most of my presentation here. And these are spin effects without polarization. And you may say now, if there's no spin polarization, how can there be spin effects in these materials? And that's actually the point that I want to make first. These materials, because of the paramagnetic states, have significant spin selection rules. In other words, the probability of electronic transitions, and that includes transport and recombination transitions, depends on the spin state of individual charge carriers or pairs of charge carriers. And that is amazing, because that you can have these effects in complete absence of polarization, because if you have a spin selection rules that depends on permutation symmetry of charge carriers. So now, in other words, if you have two charge carriers that form pairs and they form as a triplet state, and that can happen without polarization, because if you have as many triplet plus as triplet minus states, or if you have triplet zero states, then there's no polarization. But if your transition is singlet triplet dependent, and again, triplet zero and singlet both have no polarization, but if the transition depends on whether you have a permutation antisymmetric state, which is a singlet state, or a permutation symmetric state, which is a triplet state, then you can have electronic transitions. That means, for instance, conductivity processes that depend on spin. And if that sounds too abstract, let me give you an example here. So, example, a real-world example. This, what you see is a plot of actually real data, that is density functional theory data, but real data of electron and hole polaron wave functions. In other words, this, what you see here, is a display of an electron hole pair in the pi conjugated polymer MEH PPV. And that's kind of that was one of the first organic semiconductors that people have studied. You can build OLEDs out of this if you want, not particularly good OLEDs. But what I want to illustrate here is that these states are localized, even though, I mean, they're slightly delocalized along polymer chains. But overall, within a chromophore, meaning maybe several hundred chain links or monomer units, they are localized. And these localized charge carriers, if you inject into this material both electrons and holes, Once randomly these charge carriers drop below the on-Saga radius, you form pairs of electrons and holes. In these pairs, usually they are on different polymer chains, as illustrated here. And if you create that, then you basically form metastable pairs of electronic excitations in these materials. And what they can do with regard to electric currents in these materials is quite remarkable. So let me sketch you an experiment here, a very simple experiment. You build a device out of a polymer layer. So that's a layer of, let's say, 50 nanometers of MEH PPV, that polymer. And now you sandwich it between electron and hole injectors. So calcium is an electron injector, another polymer, copolymer, which is called polyethylene dioxide thiophene, or PDOT, if you dope it with PSS, polystyrene sulfonate, would be a hole injector. And then if you put contacts, let's say in the form of indium tin oxide and maybe an aluminum contact on top of it, then you have a device. And if you apply a bias, let's say battery, DC voltage, you can create a current. And then you can measure that current. So very simple experiment. And if you do that, so as I just explained, you inject electrons and hole pairs. And these electron and hole pairs, they form these metastable pairs that are illustrated in this DFT sketch. But when they form, they randomly form singlets and triplets. And they eventually, I said they are metastable, and that means for electron timescales, very, very long timescales, that means microseconds to milliseconds, whereas electronic timescales are typically femtoseconds. So a microsecond compared to femtoseconds is really very, very long. But eventually they recombine, meaning there's an intermolecular transition. And when that happens, then you have a recombination current. And that's exactly the kind of current that you see when you apply that bias. And now here's the interesting part. The current happens following this term diagram that's shown here in the lower left. I don't know if you can see my cursor. Can you see the cursor?
Yes.
Hello? Yeah,
yes,
okay,
yes.
Very good. Okay, great. So it can happen through the singlet channel or the triplet channel. What that means now for this material is microscopically, you always create these pairs of 2 spin 1/2. 2 spin 1/2 creates a very simple quantum mechanical system with 4 eigenstates, essentially the product states of the up and down. And remarkably now, if you do this experiment, so you apply your bias, you measure your current, and now you measure the steady state current, the constant recombination current that you've applied due to your constant bias as a function of magnetic field, you have tremendous changes, really on the order of percentages of this current, as shown here. This is now experimental data measured at room temperature for very, very, very weak magnetic fields. So I apply here millitesla of magnetic field. And I mean, the geomagnetic field, the Earth's magnetic field is maybe an order of magnitude or 2 orders of magnitude below this millitesla range. So these are still very weak magnetic fields. And if you, for instance, if you look here at 6 millitesla and room temperature, the Boltzmann factor is for all practical purposes still 1. In other words, the polarization of our spins is 0. There are as many spins that point up as spins that point down. There is no magnetic polarization. And yet, and that actually means if you change your magnetic field between 0 and 6 millitesla, there's no change of magnetization. Magnetization is 0 at 0 magnetic field, and it's still 0 at 6 millitesla. For all practical purposes, it may be, I don't know, 10 to the minus 6 or something like this, but that's almost nothing. And yet, in spite of no change of polarization, you have a change of your current, your spin-dependent current, on the order of percentages. And that is because these currents are not, they're spin-dependent, but they're not dependent on polarization, but permutation symmetry. We are probing singlet versus triplet states. And the question is now, why would singlet versus triplet states change? And the answer is, the short answer is, because we're dealing with a non-equilibrium system here. And so non-equilibrium means you constantly pump new charge carriers, they recombine, you have a steady state, but not an equilibrium. And if you change now your magnetic field, and your magnetic field, obviously, if you change your magnetic fields, then it changes the Zeeman splitting in this 4-level term diagrams that I show here. And once the applied magnetic fields outcompete the local hyperfine fields, so what are now the local hyperfine fields? These are the fields, the random local magnetic fields created by the nuclear magnetons of the protons. Why are there protons? Of course, there are protons everywhere because it's a hydrocarbon compound. So you have hydrogen everywhere. That means you have protons everywhere. They have a nuclear spin of 1/2. That means they randomly create local magnetic fields. And random local magnetic fields really means one polaron sees one hyperfine field with one random magnitude on the order of 1-2 Tesla in a random direction. And the other polaron that is maybe only 1 or 2 nanometers apart sees a completely different hyperfine field with a different magnitude and a different direction. And now if we apply this external magnetic field and we superimpose this, of course, to all hyperfine fields, once this outer magnetic field, the external magnetic field, outcompetes the hyperfine fields, that's when we shift the Zeeman states significantly around. That changes the singlet-triplet spin relaxation, also called intersystem crossing times. And that changes here. Now we go back to our electronic recombination diagram. It changes the electronic transition rates, in other words, the recombination rate. That changes the recombination current, and that changes the current in our device. So that's a remarkable effect. It took actually people decades to figure this out. And they're these kind of, they're also called radical pair processes. They are pretty widespread in carbon-based systems. So for instance, bird compasses, which are also of some bird, like European robins, which are also very, very sensitive to geomagnetic fields. They are based on very much the same highly magnetic field sensitive effect. So so how can we corroborate this whole story with, with one magnetoresistance curve that you see here? We cannot corroborate this. The ultimate verification of what I just explained is if you now add to your experimental setup this coil that's perpendicular to your magnetic field, and you add an oscillating magnetic field, meaning an RF field, and now you repeat your magnetic field measurement, and hopefully you can see that other data now is the green curve. The green curve looks almost the same as the red curve, except for approximately 3 millitesla. And we applied here an RF frequency of 85 megahertz. And you see there's a tiny, tiny deviation. And let's look at the difference of these two curves. And what you see here is what you actually see here is a superposition of two Gaussian lines. And these two Gaussian lines are actually the magnetic resonance lines corresponding to electron polarons and hole polarons. So we can measure by measuring an electric current in these devices, we can measure magnetic resonance. And that's one of the crucial tests of this story. So because the argument here is, if I can do magnetic resonance, I can create resonant transitions between these states. And that is essentially, that was one of the core verifications of this model. Now, what determines the width of these resonances? Of course, the hyperfine field. So the hyperfine, the widths of these resonance lines are essentially imprints of the random distribution. That's why these are Gaussian lines of local hyperfine fields. So if that's true, and these hyperfine lines are caused by the proton nuclear magnetons, then if we repeat the same experiment with the same polymer, except all the hydrogen is now replaced by deuterium, which has a 6 times smaller nuclear magneton, then we should see qualitatively the same result, but quantitatively a different result. And that's exactly what is happening. All of a sudden we see a much more narrow resonance because we have deuterium with a smaller nuclear magneton. And of course also the deviation here, the change of our current is much bigger because the hyperfine fields are more narrowly distributed. We can establish magnetic resonance with more charge carriers at the same time. So that's essentially a verification of this whole quantum system that we are probing with electric currents. And that brings me back to quantum sensing, because once we accept and understand that we have a quantum system here that we can probe with straightforward electric current measurements, then we realize we have a quantum system that has discrete resolvable energy levels. Now, is it possible to initialize this? Yes, it is, by applying a steady state. I mentioned earlier, in a steady state, you have, of course, random generation of these 4 states. But since the singlet states recombine much, much quicker than the triplet states, you basically pump singlet states as you bring the system into a steady state. And that means you initialize your system. You can read it. And that's what I've just shown. You can essentially probe the system and measure it with electric currents. And that again, now, does this really work? We've essentially repeated the experiments that I just showed, not just for 85 megahertz and 3 millitesla. We've repeated this at magnetic fields between approximately maybe a tenth of a millitesla, about a Gauss, so 100 microtesla, and approximately 12 Tesla. And so that's 5 orders of magnitude. And in these 5 orders of magnitude, if you look at the proportionality between frequency and the magnetic field, where these current blips occur, there's a perfect linearity. So you see this log-log plot here, and you see it's on a straight line. And why? Because this proportionality is only governed by a weakly spin orbital coupled electron. That means the gyromagnetic ratio of vacuum electrons, and that is only governed by constants of nature, by Planck's constant, the electron charge, the electron mass, the speed of light, and therefore we have a system with a built-in calibration. So we can convert magnetic field into frequency, and that with a conversion factor that doesn't need to be calibrated. So that's in contrast, for instance, to Hall sensors. But it's the transduction factor, the conversion factor, is given by nature. And that makes this an incredibly elegant readout method. And you see here the low-tech approach of these devices we had about 10 years ago, when we just built a thin film bipolar injection device on a piece of glass, flipped it on top of a printed circuit board, and the copper circuitry was supposed to, or did, generate the RF fields that we need in order to do this experiment. And then, yeah, so you see the data here. We sweep the frequency, see this current blip, and where that zero crossing of the current blip is, that's log-in detected. So we see the derivative curve of a resonance peak. That's where our magnetic field measurement takes place. So we take our frequency divided by gyromagnetic ratio, and we've measured our magnetic field. Since then, we've took several steps to really scale this into a monolithic device. You see nowadays we make it about 50 micrometers in diameter, and that makes it much more elegant to actually carry out experiments. So now that looks like it looks like a quantum sensor. It is a quantum sensor, however, only if we can also impose coherent manipulation. And that's, of course, the question. Can it be coherently manipulated? And the answer is yes. And let me talk about this on the following slide. So we know now from what I said earlier that if you apply radio frequency, magnetic fields at radio frequencies, we can induce transitions between the eigenstates of this quantum system. If that's the case, then I can also, if I apply coherent magnetic oscillations or coherent electromagnetic radiation on very, very short time scales, and that, of course, requires sufficiently high intensities so that the coherent spin motion happens sufficiently fast, that allows me to prepare coherent spin state, coherent quantum states. And so one experiment that one can do is illustrated here on the left. So think about, you measure your electric current, and in the steady state, as just shown, if you apply a constant bias, then of course your current is constant. And now you do not just apply as a continuous wave, an electromagnetic wave, but you apply a very brief radiation pulse. So this is basically what pulsed magnetic resonance does. So the pulse parameters, meaning the pulse length tau and the amplitude B1 and the frequency omega, then determine what kind of coherent spin you prepare. And you prepare a coherent spin state if your pulse is short enough so that it's below the coherence time. So of course you don't want your coherently prepared quantum state to relax. So you need to do it within the coherence decay. So if you do that, you prepare your coherent spin state. If you measure your spin-dependent current, then your constant current will not be constant anymore. After that excitation, it will change. And then as your system, of course, relaxes and eventually approaches its steady state, then the current will relax back to its previous steady state value. And of course, that experiment works, as the data shows you on the right. Again, same polymer, MEH-PPV. Here we deal with a frequency in the X-band range, roughly 9.710 gigahertz approximately, that causes our current change at around 347, 348 millitesla. And you see here, so what's plotted here is your current change. So what's listed here is, or plotted here as 0, is the change in current. So there is, of course, a constant offset. And if you apply these brief pulses, for as long as you're not on magnetic resonance, you see no response from the sample. That's always a good control experiment, which means our sample does not work as an antenna. That's always important. You have to build your sample that it does not just inductively absorb your radiation pulse. There's only a change when it's on resonance. And then there is this multi-exponential response that is governed by all the time constant of this rate diagram that I just showed. The important insight is now, if you see such a on-resonance transient, if you integrate this current change, of course, if you integrate a current transient over time, then you count charges. And the charge Q that you count is, because it's due to a decay of a coherent spin state, is a projection of your coherently prepared spin state onto your observable. Observable in this case is permutation symmetry, as I explained earlier. So if we now measure Q, for instance, as a function of the excitation length, then we see something that looks like this. So this here is delta Q, the change of charge as a function of your excitation length. And you see now, here we are on a different time scale. The time scale here where we integrate our current, that's roughly on the order of the dielectric relaxation time of our material. In other words, the built-in RC times of our material that allow us to see a current change at all. But if we integrate that, again, then we count charges, and now we measure these charges as a function of the excitation length. And excitation length really means now on the coherent time scale of these spins. So now we're talking lower nanosecond range, and you see this oscillation. So your current, your charge goes up and down and up and down, and the oscillation decays. And what you see there is a coherent quantum mechanical oscillation of your spins. You can basically see how your spins go up and down as you coherently drive them. And this kind of spin motion is called, this resonantly driven quantum mechanical propagation is called a Rabi oscillation. So we see here a spin Rabi oscillation. What's the proof for that? I mean, it's an oscillation. That could be anything. You will see immediately that this is a Rabi oscillation. If you slightly change your applied magnetic field, so now it's almost the same. So from 344.64 millitesla, I shifted to a little bit lower value, 343.62, completely randomly picked. And you see the oscillation looks completely different. And that is because you've changed your Hamiltonian, because your Hamiltonian is strongly influenced by, of course, by Zeeman. The Zeeman term is the most pronounced term in this weakly spin orbital coupled electron spin system. And because of a changed Zeeman splitting, your whole quantum mechanical propagation looks different now. And now you could say, well, these are randomly picked magnetic field values. How does it look at all other magnetic field values? Of course, we've repeated this, and for many magnetic fields. And you see now, here you see really now in this color plot of these repeated pulse length dependencies, the imprint of coherent spin motion of a spin 1/2 pair onto the sample current. And that really proves that if we measure electric currents, and that's a remarkable thing, we measure in a thin film device an electric current at room temperature, and we see the imprint of quantum mechanical propagation. You can immediately use this and do spectroscopy with it. In other words, you take this time-dependent data, Fourier transform it. What you see there is these hyperbolic features. The large one here has its minimum in Rabi frequency at a frequency for the given B1 field, the resonant driving fields that we've applied, at a value that is equal to the spin 1/2 nutation frequency. So in other words, it's B1 times the gyromagnetic ratio. And that shows us that we are dealing here with S equal 1, meaning spin 1/2 systems, as we would expect from charge carriers. Now, remarkably, if that frequency is at about 50 megahertz here, then the other hyperbola is exactly at twice the value. And sometimes people who don't know much about spin physics say, oh, so if 50 megahertz is spin 1/2, then 100 megahertz must be spin 1. That's actually not true, because the Rabi frequency of a spin 1 particle, something like an exciton, for instance, would actually be not at twice gamma times B1, but it would be at square root of 2 times gamma times B1. So exactly at 1.4 times 50 megahertz, and we see absolutely nothing here. So that 2 times gamma times B1 is actually a beat oscillation. So what we see, and that's exactly what you also see here in panel B, where you have these different harmonics that occur at the same time. And that is actually a proof that we deal with pairs of spin 1/2, because that's actually a Rabi beat oscillation. So it's quantum beating. And that is due to the fact that we measure permutation symmetry. So in other words, the relative orientation of spins within spin pairs. And as we drive these two spins of electrons and holes in a slightly different manner, the beating between their spin orientation is imprinted into the electric current. So that's a really, really beautiful quantum mechanical effect. So long story short, we can force our quantum systems that we straightforwardly measure electrically we can subject this to coherent spin manipulation. And that means we do have a quantum sensor. And then once we can do that, then all of a sudden we can do a whole bunch of exciting experiments that we can essentially utilize our quantum sensor to access observables that before we just did not have access to. So let me give you an example. So we all understand now this experiment that I just explained just consists of a radiation pulse, a coherent radiation pulse, then a current on long time scales. Much later, current changes that exponentially relax back to the steady state. And when we integrate these, meaning we count charges, then we see the response of our quantum system to that coherent excitation. And if we measure that as a function of magnetic fields, then we get a magnetic resonance line. Okay, so if we can do that, then we can also see Rabi oscillation, as just explained. If we change the length of the pulse, then we see an oscillatory behavior. So in a sense, you would say, oh, isn't that exactly the experiment that he just explained? And it totally is, with one slight change to the data that I just showed you on the previous slide. You remember the data I just showed you was measured at X-band, roughly 9.7 gigahertz and about a third of a Tesla. So now here we move now into a completely different magnetic field domain. Again, still room temperature. Now we are back in this domain where I showed earlier that data for this extreme magnetoresistance, meaning like a few millitesla. And all of a sudden, we can probe now coherently our spin states exactly at these very low magnetic field range, where there's practically no spin polarization. So the spins in these systems are totally unpolarized, and yet we see coherent spin motion of these spins. So, okay, so now we've repeated the same experiment at a different magnetic field. What can we do with that? Well, and the answer is, so if we now can coherently prepare a spin state, now we can essentially now we can do magnetic resonance without any spin polarization, which is what magnetic resonance totally does not allow you to do if you carry out conventional inductively detected magnetic resonance spectroscopy in the way people have done this for electron spin resonance for 50, 60 years. So it's impossible to measure with conventional EPR electron spins at 1 or 2 millitesla or 3 millitesla in absence of, and especially not at room temperature when there's absolutely no polarization. Here we can do it, and that means now we can do magnetic resonance experiments such as electron spin echoes that are electrically detected. If you do that, it almost looks like conventional electron spin echo experiments. You have a pi/2 pulse, then a pi pulse. Pi/2 corresponds to the angle by which you turn your electron spins when you coherently prepare your spin states. And then you introduce with the pi pulse. So when spins dephase, I don't want to say decohere, when they dephase, and you introduce a pi pulse, you essentially take your dephased spin ensemble and you almost flip it around like a pancake. And then they rephase, and then you get a spin echo. The only difference when you measure this by measuring spin permutation symmetries, you have to project your resulting spin state that is to be probed onto the quantization axis again. So you need another pi/2 pulse. But then you can electrically detect electron spin echoes again in absence of any spin polarization. Now, once you can do that, then you can carry out an echo decay experiment. In other words, you measure how your spin echo decays if you increase the time reversal moment, meaning tau, the tau time between pi/2 and pi pulse, and that shows you how coherence decays in your ensemble. So now we can measure spin relaxation of electron spins in complete absence of a magnetic field, which is exactly what you cannot do with magnetic resonance spectroscopy typically. Now, if we can do this, we can do other well-known pulse sequences. So that's an example here. So we go one step beyond. We take our Hahn echo sequence, which is what I just talked about, detect our spin echoes, and now we add to that sequence, in other words, we put another pulse before that sequence in order to invert our spin ensemble. So now you may say, wait a second, inversion refers to spin polarization. If there's no spin polarization, there can't be an inversion of spin polarization. And that's true, because what you invert here is not spin polarization, because it doesn't exist. You invert permutation symmetry. So if you have a steady state ensemble of singlet and triplet states, your inversion pi pulse will invert singlet and triplet states. And if you then detect your permutation symmetry state with a conventional Hahn echo sequence, you will also get a Hahn echo, except, as you see here now, for as long as the time of the inversion pulse, by which the inversion pulse precedes your Hahn echo detection sequence, for as long as that time is not too long, let's say 400 nanoseconds, then you get a Hahn echo that goes in the opposite direction. It's inverted. Now, as you increase the time, if you now repeatedly measure that inverted Hahn echo as a function of the separation time, the inversion time, eventually, after the inversion, your inverted ensemble will relax due to its return to the steady state. And that means at some point, if you, in this case, it's 800 nanoseconds, if you repeat the experiment, you get only noise. There's no discernible signal. But if you then make this time very, very big, let's say you go to several microseconds, or here, the longest time, 50 microseconds, that's 50 microseconds, the equivalent of the inversion pulse being infinitely long, or before the Hahn echo sequence, or in other words, there is no pi pulse, then unsurprisingly, you get the regular non-inverted Hahn echo back. And if you now measure this transition for all different times capital T, then of course you also get an exponential curve, except that exponential curve does not measure your spin coherence time, but it measures the longitudinal flip time, the so-called T1 time, the transverse spin relaxation time. And here we go. here we have another access to a really interesting observable that our quantum sensor provides, which we could never probe with conventional magnetic resonance spectroscopy. So with this given, we can essentially measure some of the most important observables that govern these electronic processes in this system that otherwise would not be accessible. So I realize I have about 5 to 10 minutes, and so I'll switch one gear up, and I want to give you a second and last example of the kind of processes and the kind of physics that you can probe with this kind of sensing scheme that would be entirely inaccessible with actually all other experimental or spectroscopic techniques. And these are nonlinear magnetic resonant effects, or in other words, so-called strong drive effects. So what's nonlinear magnetic resonance? So linear magnetic resonance is magnetic resonance where your resonant condition is, and that means your electromagnetic radiation that causes that resonance, is compared to the Hamiltonian of your system. And again, that's usually for spin systems, the Zeeman Hamiltonian, only a slight perturbation. If that's not the case anymore, then it's not then it's not the linear magnetic resonant regime. Now, people have been aware of this regime for decades because the nonlinear optical resonance, meaning electric dipole resonant spectroscopy, and there's a name for that, it's called nonlinear optics, that has been around for many decades, and people utilize it for different spectroscopic applications, and it's well explored. For magnetic resonance, totally not explored. Why? Because for all practical purposes, it's not attainable. Think about traditional magnetic resonance. I've said it several times now. If you want to do traditional magnetic resonance, you need polarization. Without polarization, you can't detect anything. Now, in order to get polarization, you typically need very strong magnetic fields. So you need order of Tesla or tens of Tesla when it comes to nuclear magnetic resonance. But you cannot then reach the nonlinear domain by applying resonant drive fields whose amplitude are also in the Tesla range. You'd need a radio frequency source that has megawatt of intensities. You need your own nuclear power plant to drive this source, and it would be so energetic that you would any reasonable sample would get evaporated. So if you applied these radiation intensities, so in other words, it's not attainable, and that's why people have not explored this. And now with this approach, this sensing approach, it's completely different. Here we can attain the strong drive regime not by making B1 particularly large, but by making B0 particularly small, because we don't depend on polarization anymore. Interesting, there was a theory group also about 10 years ago who figured out that if you do that, then for these spin pairs that we probe with our electric currents, really unusual eigenstates emerge under these strong drive conditions. And B1 does not only have to be on the order of B0, it also has to be larger than the hyperfine field. So that puts, in a sense, a lower limit on B0. So we cannot make B0 infinitely small, but we can make it reasonably small. That means on the order of the hyperfine fields. That means on the order of millitesla. What they figured out was that if you create strong drive with magnetic dipoles, something very analogous to strong drive effects in nonlinear optic happens, namely a collectivity of your dipoles. So for electric dipoles, this is called the superradiance or the Dicke effect, again known since the 1960s, 50s, and 60s. But for magnetic dipoles, this has only been explored basically over the past 10 years or so. And the beauty of this theoretical work was that they showed that if you create collectivity among spins, meaning you align them due to the strong drive, they all go in lockstep, then of course what you create is lots and lots and lots and lots of triplet states. And if you have spin-dependent transitions, where you essentially probe your triplet state density, because singlet transitions are allowed and triplet transitions are not allowed, you essentially completely quench your current. So in other words, your steady state current does not get enhanced, as shown in the data earlier, but at strong drive, it actually gets quenched. So that was a really, really interesting prediction. And so we immediately jumped on it and built that experiment. We used, and again, we had to make hyperfine fields as small as possible. That's how we created, or that's why we collaborated with a synthesis group that created these deuterated polymers. And if you look at deuterated MEHPPV and you apply, again, 85 megahertz, that gives you a resonance at around 3 millitesla, and then you crank up your intensity, your B1 field, you see an EDMR signal or a magnetic resonantly induced change of your current, as discussed earlier, shown here by these red areas. But if you then drive it higher and higher and higher, once you exceed your hyperfine fields, indeed, all of a sudden, the enhancement changes into a quenching of your rate. And note what's plotted here is the current. So a recombination enhancement means a quenching of your current. So your quenching of the current turns into enhancement of your current. And that was basically the demonstration of nonlinear magnetic resonance, of the spin decay effect. So not the decay effect, but the analogy to magnetic dipoles, which then the authors of that study called the spin decay effect. And it's quite remarkable that you can see that. One last effect that's also in the domain of strong drive is, of course, multiphoton transitions. So it is conceivable when you reach the strong drive regime, just an analogy to the strong drive regime of electric dipoles, that you have multiphoton transitions of magnetic dipoles. There was also, and that really goes back to the discovery of multiphoton transitions in the 1930s, except for magnetic, for in these particular magnetic resonantly excited pair systems that only happened in the past 10 years. And if you do this, you can actually make predictions for all sorts of B1 fields, for all sorts of B0 fields that occur at different resonant conditions, meaning combinations of B0 and B1. And you see, you get a whole pattern. So this is all simulation, numerical simulation based on Flocage solutions, as explained in this paper here. And you see here, that's all of a sudden, you know, what we call linear magnetic resonance is what you see at the G factor, the well-known G factor of electrons of 2 and low driving fields of B1. So it's essentially here, what's labeled here with 1, that's linear magnetic resonance, and all other, and linear magnetic resonance is everything that magnetic resonance people have dealt with in the past 80 years. And you see there's a whole new world of other effects labeled here with 2, 3, 4, 5. What we see here are multiphoton transitions, as just explained. The red one here is again the decay effect. We see other inversions analogous to the decay effect. We see shifts. So these curved lines are shifts. These are indications of Bldg shifts. And then we also see here 4, 5. These are fractional Landé factor transitions, which is also remarkable that we can see this in these pairs. Now, is this experimentally observable? And let me show you how far we are experimentally. We have to apply, in spite of having low B0 fields, still high RF powers. And eventually we fry our device. We apply too high RF powers, so that just the thermal absorption causes heating, and then our sample goes nonlinear. And this is basically what you see in these dark shaded areas. But if you look on the left-hand side, where heating does not occur yet, you see that there's a remarkable similarity. So in other words, these features are confirmed. We see shifts. In other words, we see Bldg shifts. We see multiphoton transitions. Here's a 2-photon transition. And this is very, very exciting. And that's what we are studying right now. I don't want to go into the detail because I realize I'm running out of time. Here there's, we specifically designed new monolithic devices to do these measurements. This is a quantitative confirmation here on the right-hand side of the agreement of theory. So the red line is not a fit, it's just a plot of theory values for the Bldg shift. It's total agreement with experimental data. And again, then you see here this 2-photon transition. Really, really interesting. So long story short, I need to come to an end. And I haven't heard anyone. I haven't received any questions. Am I still online? Can you hear me? Or did I talk for half an hour into a cut-off computer?
No.
Okay, very, very good. I'm glad that after my 1 hour monologue, I still have an audience. And let me summarize. So localized charge carriers in organic semiconductors form charge carrier pairs with discrete energy states, undergo spin-dependent electronic transitions that provide quantum readout, allow for coherent manipulation with E&M radiation, so we have coherent control. We have initialization that's simply due to charge carrier injection. We pump paramagnetic states that initialize our system, and we can use this to probe all sorts of observables: exchange coupling, dipolar coupling, strong drive effects. We can observe strong drive effects and see, a whole shopping list of nonlinear magnetic resonance effects, Spinbased effect, Bldg shift, multiphoton transitions, fractional G-factor resonances, and there is certainly a lot that can be has yet to be discovered. And all of this together basically is a demonstration and a utilization of a different kind of spin-based. Now I have to emphasize here, it's spin-based ensemble quantum sensing. We are working on doing this with individual pairs, but what you've seen here is an ensemble quantum sensing concept. And with this being said, I want to acknowledge my co-workers in my research group, and of course also my collaborators. John Lupton is in Regensburg. Vargas Mkhitaryan, he's basically he's in Ames, but I met him 2 months ago in Regensburg when I visited John the last time in November. Regensburg is in Germany, so in Europe, different continent. But John has always been a collaborator. But then also my Utah collaborators, Vali Vardeni and Misha Reich. Misha Reich is one of the theorists who wrote this 2013 paper describing the Spinbased effect. And then, of course, also Paul Byrne, who is from University of Queensland. They synthesized the deuterated MEH PPV. Stefan Grimme from Bonn, that's a density functional theory group. And then Hans van Tol, the high field measurements at 12 Tesla, they were not done. We did them, but not in Utah. We did them at the National High Magnetic Field Lab in Tallahassee in Florida. They have the highest magnetic fields in the world. So it's a marvelous facility. And we are using this. And then, of course, our sponsors, that's the US Department of Energy, who is paid for that research. And with this being said, I think I'm open for questions. And yes, pleasure. It's a pleasure.
Thank you, sir, for your wonderful presentation. So we have got 2 questions in inbox, so I can read those questions. The first one, what is the quantum sensor?
Meaning what is the physical implementation of the sensor? What is that sensor? So if that's the question, the sensor, the sensing device, if you want. I mean, it depends on what you call device. Of course, the device, you can call device our little monolithic layer stack or so, and can call from a technological point of view, you can call that the sensor. But what actually senses, what transduces your observable, that is these Coulombly coupled, metastable, localized electronic excitations that of electrons and holes that find themselves. So you have an electron and a hole. They at some point they are just coulombically attracted. They move closer and closer and closer. And let me go back to slide number 2 because that's actually slide number 3. No, slide number 4 here. So top left, they get closer. They get as close as possible, but close as possible is not 0. because in all likelihood, when they are generated, they are on different polymer chains. And then they can move within these chains with reasonable mobility. But once they hit, it's like beads on a string. They can move along that string, but once they hit the closest proximity, they cannot get closer because intermolecular transitions, as I said, they take place on long time scales, microseconds to milliseconds. And that means these pairs, these two spin 1/2 pairs, they are metastable, even though they're only excitations. And that's our sensor in that sense. That is the actual sensor that transduces the quantum information into a electronic charge transition. In other words, into the current that we can then detect and measure.
Thank you, sir. We have another question. What is the spin selection rules?
Yes, that's a very good question because I didn't spend too much time on explaining that. So a spin selection rule means that the matrix element for an electronic transition, so electronic transition is basically everything that makes the electron do something in a very naive way explained. So an electron can be in an excited energy state and basically energetically cascade down without moving around just by losing energy. That would be an electronic transition. But an electron can also actually not lose energy and just move spatially. Then you have an electric current. So these are all electronic transitions. Now, in a lot of materials, electrons can do all that without any consideration of spin. So it doesn't matter what the spin state is. The electron can do that. Now, when you have a material where you have weak spin-orbit coupling, I mentioned this at the beginning, that spin-orbit coupling is weak in these materials. So in other words, the coupling between the orbital angular momentum and the spin of an electron is very, very weak. Why would that be weak? The answer is because the charge of carbon, because carbon is very high in the periodic system, so the charge of carbon is very small. So carbon, carbon nucleus has a weak Coulomb field, and that's why electron orbitals are not too curved, and that leads to a weak interaction of the magnetic field produced by that electron that goes through this orbit, and that translates then in weak spin-orbit coupling. And now, if the coupling between the orbit and the spin is weak, that means the total angular momentum conservation, which that's a conservation rule that always has to be met, breaks down now into two conservation laws, a spin conservation law and an angular momentum conservation law. Now, and that means if you want to have an electronic transition, such as an electron moving, so in other words, a current, then that current requires that when it happens, that the spin must be conserved. And if you look now, for instance, to these singlet and triplet recombination channels here, if you have a singlet state and it decays, well, the ground state of an excitation is always a singlet state because that's Pauli exclusion rule. So you always end up in a singlet state. That means now if your singlet decays, your singlet polaron pair decays and recombines, that's an allowed transition. A singlet undergoing a transition into another singlet state doesn't require a change of spin. So it's an allowed transition. But if you have a triplet state and you want that triplet state to decay, it can only do that if you have some sort of spin release. So in other words, that can only happen if that triplet interacts with something to give away its spin, because otherwise you would violate spin conservation. And that's an example of a spin selection rule. So the nature of your system requires that your spin manifold has a certain permutation symmetry for the electronic transition to happen. And yeah, that's a spin selection rule. And what that means now is, if you generate singlet pairs and triplet pairs randomly with equal probability, the triplet pairs will not decay, whereas the singlet pairs will decay. And that means now in the steady state, as illustrated here with this big Gaussian and small Gaussian, the triplet state density will be very, very high. You just pump triplet states. while at the same time, even though these are totally random processes, you don't pump singlet states. And that's what I meant earlier when I said, just by applying a bias and bringing the system to a steady state, you generate, you initialize your quantum state. You generate well-defined initial quantum states that you can then coherently manipulate. So that's what spin selection rules do for this system. And again, that's all only because they're made out of hydrogen and carbon. If you make it out of silicon, you still have spin selection rules, but much less because silicon is one period down. If you create a semiconductor, let's say you take gallium arsenide, there are no relevant spin selection rules in gallium arsenide because the elements out of which it is made are just too heavy. In fact, spin-orbit coupling goes with the force power of your atomic number. So in other words, carbon, I don't know what the atomic number is, maybe 8 or 10. And then you go, I don't know, to transition metals, and you have atomic numbers of hundreds, take it to the force. So you have like millions of times of higher spin-orbit coupling, and then you don't have spin selection rules anymore.
Sir, thank you. We have another question. So, sir, could diamonds be a good spin-based quantum sensor?
Excuse me, I didn't completely get that.
Okay, so I have added the question in the screen. You can also see. The question is, could diamonds be?
Could diamond be
a good spin-based quantum sensor?
Oh, yes, absolutely. Diamond is, and it's of course not the material, but what the paramagnetic centers that you find in diamond. So diamond is a really good spin sensor material. In fact, the most widely used at this point. That goes back to the NV centers. Now, why is this? Well, for the same reasons that I just explained. Diamond is based on carbon, and carbon has a low atomic number. So you have very pronounced spin selection rules. And now you also have in the form of these NV centers, the nitrogen vacancy centers, you have paramagnetic localized point defects due to the paramagnetic electronic states. And this system has very pronounced spin selection rules, and now in contrast to the polymers, the NV centers, you cannot detect electrically. People have tried it, but it doesn't work particularly well. But you can really well detect those with nano-optics, and with nano-optics you can then very easily and straightforwardly detect individual spins, and that is exactly what has caused this. I mean, I think it's fair to say a technical revolution using NV centers for quantum sensing, for magnetometry, thermometry, and so there's a whole bunch of observables that you can probe with these spin centers. Yeah, so the answer is yes. Diamond is great. Has disadvantages. First of all, optical detection is oftentimes not as straightforward. So rather than having these monolithic devices that we build, you always need a nano-optic setup of some sort. And the other issue is, of course, diamond is not straightforward to handle. It's complicated, expensive, and the localization of NV centers is not great. So you don't have this lattice side accuracy, and that's what people have been struggling with. But of course, these struggles exist equally, if not even more, for polymers, for polaron pairs in polymers, of course, no question.
Thank you, sir. This may be the last question. So how can we use quantum sensor for fundamental physics research in neutrino mass measurement, etc.?
Oh, mass measurement. Oh, for mass measurement, I don't know if there's a good quantum sensor, and of course, not all quantum sensors are spin-based. I have to, because when we talk about mass measurements, and accurate mass measurements, I immediately think about, did people use any quantum sensors in the context of the Avogadro project? Because that's one of these fundamental constant of nature kind of, people wanted and have created a new mass standard basically based on silicon atoms. And I wonder if but I don't think that the quantification process of the number of atoms in this new kilogram standard were in any way determined by quantum sensors. So for quantum sensing, I don't have a straightforward answer to that. You may want to look into this reference. There's a really good overview paper about quantum sensing. That is this one here. You can still see my screen, right?
Yes.
Yeah. So it's this reference here. That's a paper by Degen, Reinhardt, and Capellaro from 2017. I would say that's the ultimate quantum sensing paper if you want to get an overview. And because they also discuss a whole bunch of other atomic physics-based, so not just spin-based or condensed matter-based, but atomic physics-based quantum sensing approaches. That paper may give an answer, but I'm not right away aware of it when it comes to the context of mass sensing. Of course, for all other observables there, as I mentioned already, of course, magnetic fields, I think we've exhausted this now after this talk. There are many approaches for thermometry also. Oftentimes thermometry also works by detection of spin relaxation time. So you measure spin relaxation time similar to this pulse excitation scheme that I showed earlier. And if you can measure T1 times, the longitudinal spin relaxation times, then most of the in many systems they are driven by phonon scattering. And so if you can detect phonon scattering, you can detect phonon densities. If you can detect phonon densities, you can essentially measure temperature because heat is phonon excited phonon ensembles. And then you have temperature, quantum sensors for quantum thermometers, if you want. And in particular, NV centers, they have proven to be extremely useful. So people have, for instance, measured NV centers in nanodiamond that they inserted as local probes into living cells. And so that's a way of doing thermometry in living cells that you could not do in any other way. How do you determine the temperature of a cell accurately? For a cell, let's say a human cell that needs to be at around 37 degrees C, and it makes all the difference if it's 38 degrees C or 36 degrees C. How do you measure that on an individual cell? Quantum sensors can do that, and that's absolutely remarkable. Yeah.
Thank you, sir. I have got 2 more questions. So if we allow, we can discuss about those questions.
Yeah, absolutely.
Okay, so first one, what is the scope of researching in particle physics in current scenario?
And I'm totally not a particle physicist. So now I'm basically talking, well, but of course it's not that I don't meet any particle physicists because I'm a chair of a department of physics and astronomy, and we do have a number of particle physicists. And yes, there has been discussion about quantum sensing schemes in the context of some of the particle detection experiments that exist. So and now how this exactly is supposed to work, I would put myself on thin ice. I know that in the context of neutrino detection, people have discussed certain quantum sensing schemes. Again, none of these, I don't know, but most of these are not based on spin quantum sensing. Again, this overview paper that is still on the screen that I have opened here right now is that makes a really good summary of what for particle detectors. I know that also for gravitational wave astronomy, which is a really young field after this breakthrough a few years ago with the LIGO collaboration, that people are exploring quantum sensor techniques for very, very, very sensitive detection of distance changes between the mirror distances in these gravitational wave detector Michelson interferometers that they are using. They have these gigantic Michelson interferometers, and they, of course, detect minute changes in interferometry. And if you have more sensitive sensors, which is what, in principle, quantum sensors are, then you can improve these facilities. But then, again, if you want to have detailed answers to that question, look into that paper and those that cited. And ultimately, these are different research areas from what we are doing.
Thank you, sir. And this may be the last question. So how to apply for PhD at CERN in particle physics? Though this is not exactly related to this webinar, but you can answer.
How to apply for a PhD study in particle physics?
CERN.
Oh, at CERN.
Yeah,
okay.
for PhD at CERN in particle physics.
Yeah. So I can't speak for CERN. Even though I've been there and visited this place, I did my undergrad studies at the University of Heidelberg, and they, at the time, and I think still today, they have research groups that carry out their experiments at CERN. So I've been there. Now, CERN is essentially a gigantic collaboration. In other words, this is not just one institute and has and everyone who works there is an employee there or so. Many people who work there because they are paid by their home institutions that are collaborators at CERN. So if you're interested in working as an experimental high energy physicist, then I would say start with look at CERN. I mean, go online and look who's collaborating there, who are the different collaborating groups, and of course also within CERN there are many different collaborations. So we must not forget that the LHC, the Large Hadron Collider, has 4 main detectors. They are separate, independent collaborations. And then there are many other facilities and collaborations that are centered around this. So there are many different ways to end up, how you can end up working there. And so long story short, once you identify the groups that work there, look at the associated institutions, meaning universities, and then apply directly to the PhD programs of these universities. And that's how you can end up being a graduate student who will end up carrying out an experimental PhD thesis at CERN and at the Large Hadron Collider, then potentially. So that would be my answer. Yeah.
Thank you, sir, for your wonderful presentation and nice discussion session. I think our students and viewers have learned a lot of things, and the main aim of our program is to motivate our students. I think by your lecture, they must have motivated, and hopefully in near future they join in this nice field. So thanks again for allow us to arrange such an important webinar.
Thanks for having me. I've thoroughly enjoyed it. Thanks for all the questions, and thank you for your interest. And I send my best wishes for your seminar series. It's a great idea.
Okay.
Yeah.
It's my pleasure.
Take good care.
Have a nice day. Good night, sir.
Thank you. Thank you. Have a nice day. Bye.